Good afternoon, good morning, good evening. Uh, I am Anis Rahman, and on behalf of the American Association of Bangladeshi Engineers and Architects, it is our pleasure today to have an expert exchange on Padma Bridge. Our keynote speaker today is Dr. Sufian Khondker, PhD, PE, DWRE, and ASCE. He will present a talk on the Padma Bridge that has recently been completed and opened in Bangladesh. The Padma Multipurpose Bridge, or in Bangla Padma Bahumukhi Setu, is a two-level road rail bridge across the river Padma in Bangladesh. Constructed in Bangladesh with her own resources, the Padma Bridge connects Lohojang Munshiganj to Shariatpur and Madaripur, linking the southwest of the country to northern and eastern regions. So this is a miraculous, marvelous achievement for Bangladesh, and that is the topic of today's expert discussion by Dr. Khondker. Dr. Sufian Khondker is a renowned engineer of water-related architectures. He is well known all over the world for his expertise. He is a professional engineer with 50 years of experience in water resources and geotechnical engineering. He is a pioneer in Scour evaluation at bridges. The United States Congress has recognized him as a world-renowned engineering expert and for his countless contributions to the field of science and technology. He is an expert panelist on flood issues in South Asia for the Voice of America. He is also an advisor to Bangladesh Atomic Energy Commission for reviewing and designing of the first nuclear power plant in Bangladesh. He is recipient of countless awards, including prestigious Albert Nelson Markey Lifetime Achievement Award, which is presented to individuals who have demonstrated exceptional leadership. So, without further ado, it is my extreme pleasure to invite Dr. Khondker to present on this Padma Bridge.
Thank you, Anis, for your glowing introduction. I am really honored that you have invited me to present a paper on Padma Bridge, which is one of the greatest achievement of Bangladesh. So my presentation is a PowerPoint presentation. Now I would like to share the presentation with the audience.
Yes, please.
How do I share? Do I open first, then share?
If you have problem, I have the presentation. I can run from here as well.
Yeah, why don't you do that?
Okay. So
That's good. Can you go in the full screen?
Okay, this is the first slide.
Okay. Thank you, Anis, again. Sorry about the technical. I always have this problem with the sharing of the screen. Again, as I said, June 25th, 2022 is a glorious day for Bangladesh. That's the day this Padma Bridge, which is I consider as one of the wonders of the engineering, was inaugurated. So we'll talk about that bridge. The title of my presentation is the Padma Bridge, the civil engineering marvel of this century. Now, the Padma Bridge is obviously across the river Padma. So I'm going to start talking about the river first and then correlate with that. As you can see, Padma River is the third largest river in the world after Amazon and Nile River in terms of flow. However, in terms of sediment transport, Padma Bridge is the largest in the world. And Padma Bridge in this region or the portion of the Bangladesh is called Braided River. I will explain what it is. Next, please. Now, all the rivers in the world, we river engineers grossly divide into three categories. The first category is shown in the left-hand side is what is normally known as the straight river. In reality, there is no straight river in the world, but these are the straight river normally in the mountain region. When at the inception of the river, it is very narrow, straight, and coming through the mountains. So that is considered the straight river. And as we all know, the rivers has two functions. One is the discharge of flow and transportation of sediment. In this area, the primary function of the straight river is basically erosion. They erode and makes the channel. When the river enters into the floodplain, it has more wide land, so it started to winding around, and that portion of the river we call meandering river. So meandering river has both the function. In some places it's called scour, and some places it causes deposition. The third category of the river is the braided river. And these are the major three categories of the river. Next, please. Now, meandering river, as I said, majority of the river in the world is a meandering river, and it follows certain rules of the nature. As you can see at the bottom, I have shown, it's kind of a wavy action. We have a wavelength, we have an amplitude, and pretty much the meandering river follows that. Although it is exaggerated some places, but it is within that confine we find most of the meandering river. And we also know the characteristic of the meandering river. For example, the outer side, what we call the outer bend always going to scour. On the other hand, the inner bend is always going to cause deposition. This is a well-known fact. And also the meander moves downstream at a rate which varies. Once we know that, for the river engineer, it is much more easier to control a meandering river, knowing those phenomena well. Okay, next look into the braided river. Braided river is, in single word, is a nightmare for the river engineers. It doesn't follow any natural laws. Sometimes it has a bend, sometimes it is a straight. It has multi-channels, as you can see. One day it is flowing on the right bank, the next day it will be on the left bank. In other words, It cannot be predicted. It does not follow any laws of nature. In addition to that, the Braided River carries the largest volume of sediment and flows. So, as I said, simply, this is a nightmare for the river engineers. Unfortunately, Padma Bridge, where it is located over River Padma, is the braided portion of the river. As I said, next one. As I said, the plan form, the river configuration changes quite frequently. I'll just give you a couple of examples. In 1967, as you can see, this was the location of the bridge. This is a narrow section of the river. Width is much smaller. So it would have been nice to build in 1967 with the narrow, but the moment with the years, as you can see, in 1980, the width of the river has increased substantially and island has started to form upstream. So that is the major change. If I go to 1995, as you can see, the river bridge location, the width has reduced a little bit, but a big island or sandbar is formed upstream that split the flow into two. And the current location where the feasibility study was done by JICA, you can see the river is a little wider. Island has dissipated quite a bit. It is moved upstream. So this is the problem of a braided river. You cannot predict how to keep this river within the confine. Otherwise, you will have a bridge here and the river away from the bridge, empty. So that was a major concern. This is the feasibility was done by JICA, and they have decided to build a bridge at that location. Of course, to confine the river, you will have to protect the river. Otherwise, river is going to wander around and we may end up with a bridge which has got no water underneath it. So those are the major concern as far as the river is concerned. Next. Let's look into what are the major design parameters for the Padma Bridge. This is as Anis already mentioned, this is a two-level truss type bridge with pile foundation. Pile foundations are deep foundations. It carries a tremendous amount of water, 148,000 cubic meter per second. That's the amount unbelievable. Then the bridge has a clearance or a headroom, what we call, of 18 feet, roughly 60 feet from the bottom of the bridge to the highest water level, so that the ship with the height of 60 feet can pass. That is the international requirement, so that the international ships and others can pass. The bridge has a 42 piers, and this is another major concern was the scour. At the piers, it has been computed to be 62 meters, unheard of. I have been in the scour business for a while. I have never seen or saw or even been able to see this magnitude of scour of any rivers. The piles is another, those deep foundation, the supporting foundation, the piles is the largest ever constructed in the world. On the average, it is 122 meters. Never heard of. The bridge was also designed for seismic event, Richter scale 8, which is a large seismic event, as you can see. Throughout the history of Bengal, only one time, the 1950 seismic event in Assam was equal to 8 Richter scale. And as you probably know, that has created a lot of problems. Even the major river, what we call Brahmaputra Jamuna, that shifted its course. So that is the biggest event ever. So this was designed for ever recorded biggest seismic event in Bengal. So even with that kind of earthquake, the bridge will stay intact, but none of the buildings in Dhaka city will stay. So that is the kind of thing we are talking about. Another major design criteria is the river training. As I mentioned, Braided River is very difficult to train. It keeps on changing course, and it is a very difficult to contain the river within the confine of the bank. And since there are many navigational requirements also, the bridge was also designed for the impact from a 4,000-ton ship or barge. If it hits the pier, nothing will happen. So these are the criteria, extremely stringent, are very difficult. In terms of configuration of this bridge, this is a truss and priestess. The top part, where is that 2 lanes and 2 lanes, 4 lanes with a divider. This is a precast post-tension concrete piece. And then this is the steel truss supported. And this is a 2-level bridge, as we mentioned. And the lower level, there is a single track for the railroad, and that is compatible with both meter gauge as well as broad gauge. So this is the superstructure of the bridge. Next. Now let's talk about the foundation, which is the most critical for this bridge. As you can see that these are the deep foundation or the piles. Then this is the pile cap, and this is the pier. There are 2 bearings on top of those 2 bearings. That superstructure I just showed will rest. Now, what is the weight of that thing? This is unheard of. The total weight per pier will carry is about 10,000 tons. So as you can see, this pile has to carry individually roughly 1,600 to 1,700 tons per piles. Never ever heard of. Most of the bridges, they design the piles maybe 50 ton, 100 ton, 200 ton, maybe maximum 300, but 1,600 ton per pile load is first time in the world. Now let me try to correlate this pile foundation to the soil characteristic. This is the soil characteristic, general soil characteristic of the Padma Bridge. As you can see, that the top 20 meters is basically muck and silt and things like that. It has very limited capacity. It says that how many blows of a hammer will take to penetrate 12 inches or 300 millimeters. So as you can see, small. So this is very soft type of thing. We cannot build there. Then from 20 meters to 60 meters is fine sand, which can carry good loads. But from 60 to 118 meters, as you can see, has a tremendous capacity. How these piles take the load, carry the load, it's by the skin friction against the soil, against the piles, the skin friction, as well as point loading at the end. So the way it was designed, that the end of the pile will be in this layer. Above that, just below that, unfortunately, as you can see, the soil characteristic is so poor. This is a clay layer, stiff clay. As you can see, it dropped so much, its capacity from almost, I can read it, 250 blows per 30 millimeter to again back to about 20 to 30. So obviously the goal is to put this pile above this layer, within this, mostly within this layer. And that's the way originally the foundation was designed. Next, please. This is the detail of the pile foundation. As you can see, there are 6 piles, all battered. Why it is battered or inclined? because then only it can take the horizontal load. Vertical cannot take the horizontal load. Incline can take the horizontal load generated by seismic event. So that was required, as you can see, the pile caps and everything. Next. Now, the piles are actually steel tubes, and the size is unbelievable. I'm going to talk about so those inside those steel pipes, there's a filler material. So the top part is a concrete, then the majority length is a compacted sand, then we have concrete again. This is a trimmy concrete. This concrete was poured underwater, and the end is a plug so that soil cannot get in there. It is a solid structure. So these are the infilling for the piles. Next, please. These are the piles, as you can see on the left-hand side. Just look at the size compared with the human being. This is a 3 meter, 10 feet diameter pipe. Never ever in the entire world they have even thought of this size piles. The maximum we use is 24-inch diameter, 3 feet maybe, but 10 feet diameter pile is unheard of. There are 6 in the original design, and also the thickness. Normally in a steel pipe, we use half-inch thickness, maybe 1 inch. This is 70 millimeter, which is equal to 3.75 inches. Never, unbelievable. Never has been done in the world. But the problem showed up because you cannot, the generic characteristic of the soil I have shown, but when they started to build these 42 piers with the piles, they had to take soil boring for each one. And they found out that 22 out of 42 does not have the required soil strength to carry 10,000 tons. And that was a real nightmare. And those piers are primarily located on the Mawa side. And that was a biggest shocker, that how to improve the capacity of the piles. Many consultants are brought in from England. One consultant is very well known, it's called Cowi, C-O-W-I. They're Danish, but they have office in New York also. I have worked with them. And I worked with one of their engineers, his name is Ben Gurwick. He's one of the best in the world in this kind of structure. He was responsible for designing that offshore oil rig in the North Sea, the most difficult one. I have used his expertise in one of my projects. I know those are the good people. But after spending a few months, both of them, consultants, said that they have no solution for this situation. And then what? Then, of course, I think we had the outside consultant, Robert John Vases, I think his name. He was originally with the designer of this bridge is AECOM. AECOM with a employee of 120,000 employees. AECOM is the largest engineering firm in the world. I have worked with them both as a cooperating partner as well as against each other. My company, ARCADIS, is not that big, but they have about 28,000 employees and annual revenue of over 4 billion. It is a Netherlands-based company. We have worked together. I know many people from AECOM. So AECOM was the designer for this. Then it came to that these 6 piles will not carry the load. So we have to consider adding one more at least. This is the number 7 pile was put at the center. That was a vertical. That had improved the capacity, and almost 11 of those 42, 11 sites were done with the additional. Still, we had to come up with something unique solution so that we can improve that friction. As I said, the piles are carried by the friction. How the friction can be increased, that is what people are looking at. In Australia, in 2 of the bridges, they have done what is called skin grouting method to improve the surrounding soil so that the soil will offer larger friction and the piles will be able to carry more load. Next, please. Conceptually, I have shown this one, how the skin friction is improved through skin grouting. Normally, as you can see, this is the solid pile. Then they have kind of a double tube. And there you pump grout means cement and sand, and that is a perforation. Those goes here through there and goes into the soil, and they then improve the surrounding soil and increases the friction. This is the concept, and it is done in 2 stages normally. But in Padma Bridge, we already had the piles fabricated. This pile was already fabricated. We had no way of doing this in Padma Bridge. So the idea came up, innovative idea was to weld a channel on the outside of the piles, have the perforation in that channel or a plate, then you pump grout, then those grout is a mixture of sand and cement, will go out through the piles under pressure and create a circular, the soil around it will be improved and it will be able to take additional loading. Again, as I said, only in Australia, 2 bridges, they have adopted this one. It is a very rare situation. In Bangladesh, the biggest problem was that normally those grout goes into the pore or the opening between the soil. But in Bangladesh, the soil is so fine. So you can't use the normal sand to generate that grout. So they had to get a fine cement from Australia, and that used kind of a fiber particle, very fine particle, and mix it. And that's the way they did. And that's the way it was done. It was a very, very innovative solution. And that really was unbelievable. But again, the other problem was, as you can see, how to drive this size of pile. Standard hammer cannot do that. When we are constructing the Jamuna Bridge, the Jamuna Bridge diameter was smaller and the depth was only 80 meter maximum. In here, diameter is 10 meter and the depth is 122 meters. And so the 2 hammers used in Jamuna Bridge could only drive this pile only up to maybe 60 or 70 meters, but they could not do any further. So a special hammer was designed and fabricated in Germany just for this project, was brought in here. That was the hammer was used to drive this pile for the additional length. And this is, again, nowhere in the world you have this kind of a hammer. And this is what for the first time was used in Bangladesh for the Padma Bridge. Next. Now, another concern I also mentioned before, the scour at the pier. As this is the river, one of the most difficult river. At the peak flow, the velocity has been measured between almost 4 meters per second. It is unthinkable. Yes, Amazon probably has a velocity higher than this, but nothing has been built in Amazon. But this is the river. The velocity could be so high that Scour could be tremendous. For the Scour computation, Bangladesh government hired a very special company. It's called Northwest Hydraulics, Canada-based. They have office in America also. I worked with them very closely. They have done Scour evaluation, this kind of model study for me in at least 4 or 5 of my projects. I know them, they are principals, and we are very close. Dick Galley was the principal. On my invitation, he came to Columbia University for an international conference on Padma Bridge. So I knew that we are in good hands. And when the computation as well as the model study came, that the Scour could be as high as 62 meters, that was shocking. So, and that's what these piers had to be designed for a potential 62 meters Scours. Next, please. Now, what is a Scour? As I said, I have quite a bit of experience on the Scour evaluation. I give lecture for the bridge engineers and highway engineers in the United States, train them. This was not very well organized effort even in the United States prior to 1980s. Next, please. Next, please. As I said, even in the United States, there is no clear-cut methodology or organized program to evaluate the Scour, how the Scour happens, what can be done, what are the countermeasures. But in 1980s, 3 major bridges failed in a span of 2 to 3 months. The most renowned one was the Schoharie Creek Bridge in upstate New York, that 10 people were killed. Then the government, as well as the federal administration, started to scream that we have to do something. Next, please. So there was a crash program taken, that we have to come up with a program to evaluate the Scour. So American Society of Civil Engineers formed a task committee under the leadership of Professor E.V. Richardson of Colorado. I was a member of that task committee, and I personally used to know E.V. Richardson well. So we worked together with many other members and came up with a document which is known as Hydraulic Engineering Circular, HEC 18, which is evaluating Scour at bridges. And that is now used in United States and Canada as the Bible. Every engineer follows that. We also evaluated almost 500,000 bridges in the United States. As you can see, most of them low risk, but 5% of them is Scour critical, can fail. So we take a crash program to provide countermeasures so that in the future, the failure to the existing bridge is brought back to absolute minimum. Next. Now, Pier Scour, how it happens? What is the mechanism? We have a flowing river, as you can see, this is the velocity profile. All of a sudden, it hits the obstruction. And when it hits the obstruction, then the flow gets separated on both sides, and it creates a kind of a vortex. Which one we call it, because of the shape, we call horseshoe vortex. And that lifts up all the soil here, and this ambient current will carry those and create a big hole around the pier. And that is simply the Pier Scour. Next, please. I just showed one example. This is a large bridge in the New York thruway system, Castleton Bridge over the Hudson River. As you can see, this is the pier. And there is a Scour here. And there is a big Scour on the downstream side also, which is a mystery. But again, I have some answer to that. That's another story. Next, please. As you can see, the scour hole was substantial. And we looked into very closely, and we found out the reason of this scour was a little different. It is the rejoining of the separated flow that caused this scour. Next, please. Now, this is the way we compute the scour. The scour has got two components. One is the natural component, this yellow part, as you can see. That will happen in all rivers, whether you build a structure or not. That we call the contraction scour. When the river width reduces, then the flow, things like that. This yellow portion will always happen, irrespective of any obstruction or not. And the next, when you start to build any structure, for example, pier, the abutment, then we impede the flow pattern of the river, we intercept the streamline, and that creates the vortexes, turbulences, and creates additional scour, what we call local scour. As it is shown in the pier, this red part is the local scour. When you do combine these two, then that is the total scour. So any structure has to be built below that level. And this is exactly what it is that Padma Bridge scour conceptually presented. As you can see, that contraction scour, general scour was 15 meters, and local scour, due to the obstruction of the pier, was 47 meters, total 62 meters. Now, as you can see, this pile length, this 62 meters does not contribute. If this scour would have happened, this 62 meters of the pile will not help carrying any load, because there is no friction, it is water. So only the bottom 60 meters is carrying that load of 10,000 tons. And that's the reason we needed such a long pile at Padma as opposed to the other bridges. Now, one question comes to my mind all the time, that instead of considering that, okay, we'll allow for the 62 meters of scour and we'll design the foundation for the remaining. My question was that why we are not looking into protecting the pier against the scour. That way, we don't have to consider the top 62 meters as sacrificial. If we can protect the scour, then of course, those portions of the pile will also carry additional load. And the protection or the countermeasures for the pier is well known. On the left-hand side, we are showing that at the bottom, the sandbags, geotextile bags, fill it up. Then normally they use riprap, is big stones or things like that. But criteria is that it has to be flush with the bottom of the river and it can be protected. And if we do that, this kind of protection, then we can utilize this 62 portion, this 62 meters of the pile will also carry load. So that's one thing I think our engineers should look into. Also in Bangladesh, just 1 second, we have improved this concept of riprap and this and that. We have introduced a very innovative scour protection design. This is called articulated concrete blocks, individual blocks, laced together by a polyethylene. And this acts as a one unit, flexible, and it can protect scour. This is what we have introduced at Rupur power plant. Next. Now, one of the answer I got from one of our Buet friends that they did not consider the scour protection because the concern was that that kind of scour protection, if it is protruding above the bed, might impede the fish migration. Obviously, we don't want that. Ilish fish, but in English, they mispronounce as hilcha. well known. The Ilish of Padma River is well known, and that is the favorite of all Bangladeshis, all Bengalis. Of course, we don't want to impede the migration of Ilish fish, and there is a big opening between the piers. I'm convinced that that will not happen. I just wanted to give one example. This is Wuhan. I was there. I had an international conference called IPWE, International Perspective of Water Resource and Environment. And I also went to visit the largest hydroelectric power plant in the world, which is the Three Gorges. This is the largest ever built. They had a similar problem. The problem was that they had a most famous is the sturgeon fish, which is actually the egg of that is the caviar. So how that fish will go upstream? This is a solid barrier. This is not like Padma Bridge, no opening at all. So they devised one we call fish ladder, sometimes fish elevator. So the fish will come from the downstream to the upstream. But it did not work that well. So what they did is that they created a hatchery to artificially culture that sturgeon fish, and they introduced on the upstream side. Now the upstream of the river is also full of the same fish. So there are solutions to each and every problem. But in Padma, I don't see the migration of the Ilish fish will be a problem at all. Next. Now the next major effort was how to keep this braided Padma River within the confine of the bridge. As you can see on the left bank, defined by the flow direction, left bank there is a protection along the bank, and on the right bank is a longer protection so that the river is always within, like a funnel, it is under the bridge all the time. And this was a major, one of the largest effort to train the river within the confine of the bridge opening. How it was done? Next, please. It was a massive effort. I was amazed the way it was done. What was done that the river was first dredged about 28 meters to take out all the mucks and the soft and the mud, everything was taken out. And they went up to 28 meters because that was the capacity of the two dredger in Bangladesh. Once they remove all those things, then they fill up that big hole with geo bags. These are geotextile filled with sand. In 3 layers, they filled it up. Then on top of this layer, next one, they started to put the armoring layer, or the top layer, what we call the armoring layer. Those are concrete blocks, each weighing about 165 kg. Because the velocity is so high, it has to be individually very big, and some pavement were done. This is a massive, massive effort. So the concept is already there. This concept at a lower scale could also be done at the piers to protect the piers. Next. As you can see, the finished product, this was done by a Chinese contractor, Sino Hydro. And until today, the total cost of this river training work is approximately $1 billion. Never ever in the history of bank protection such an amount of money was spent. But Padma is not a irregular river. We have to remember that. This is a unique thing. The next important design parameter is the seismic design. How do we design this massive structure against seismic event? As I said, it was designed for 8 Richter scale. As you can see, there are 2 components of the bridge. We have seen that this is pier and the pile foundation. And then the top part is that truss and girder and the thing. Now they are connected. If we connect these two with a fixed bearing, most of the bridges are fixed bearing, then what will happen? The earth will shake, and that will shake the pier and the lower part. But the top part cannot move with that. It is fixed, so it will bend or break. It will fail. So what do we do in a seismic design? We want to isolate the superstructure from the substructure. And we can isolate that so that the bottom part will move with the shaking of the earthquake along with the earth movement, but the top part will stay straight. It will not move because of the isolator. This isolation can be achieved through a very typical bearing, and that bearing, next please, is called friction pendulum bearing. Next. This is the friction pendulum bearing. As you can see, it can rotate. And this bearing was used for the Padma Bridge, 2 in each pier. And again, anything I'm talking about is a monstrous size. Each bearing has to carry a load of 5,000 tons. Nobody ever heard of. This is one of the largest bearing system was ever designed and built. It was built in Wuhan, China. But during the testing, one of the bearing I heard that had a little problem. So they sent that particular bearing to a lab in San Diego, United States. They have the special lab to test this one, and that was tested in San Diego lab. So this is again is a unique bearing, never done before. First in Bangladesh. Next. This is the actual picture of that bearing when the cover was taken out. Next. So that was the criteria of the seismic design. The last criteria this bridge was designed is that this river has ships, barges, and primarily ferries. Because of the very high current or whatever may be the reason, they can ply loose and hit the pier. Then what will happen? Each and every pier was designed to take an impact load from a 4,000-ton ship or barge. That is not there in Padma yet, but it was designed for that. Recently, there is an event. One of the ferry hit the pier, pier number 17. Nothing happened, but again, as a result of the impact, the people in the ferry was injured, but the bridge has nothing happened. So these are the challenges were offered for the Padma Bridge. As I mentioned initially, that my title of the topic was, this is the engineering miracle of this century. So I will share one project, which is also considered as the engineering miracle of the 20th century. And that is the Zuiderzee project in the Netherlands. When they were building there, I was studying in Netherlands, and they took us 2 or 3 times to see how massive this structure is and how it is being built. There was a tremendous education for me, particularly. I have never seen such a big structure. And again, we talk about cost of Padma Bridge and this and that. When they started this Zuiderzee closure project, there was no precedence in the entire world. Nobody knew how much it can cost. So the government, Dutch government, gave a blank check to the engineers. Don't worry about the cost. Go ahead and do it. And this was a unique design. It was done. They don't tell for sure, but the rumor is that the cost of this structure in 1970s dollar was between $16 to $20 billion. Next. Now, As I mentioned, the American Society of Civil Engineers, ASCE, is one of the largest professional organizations in the world with over 150,000 membership and 77 countries, including Bangladesh. They are responsible for providing the grades for all the bridges and roadways in America. They provide the grading, and that becomes the basis for the US government to allocate money to repair on, and ASCE is very much involved on that. ASCE also does one more thing. They try to identify the greatest civil engineering achievements, and they identified those projects. These are the 7 wonders of engineering they have identified for the 20th century. That includes that project I said, Delta and the ZZ project that was completed in 1997, and that is also considered as one of them. Now, I think Padma Bridge qualifies for that. Why? Next, please. Because number one, the bridge is over the most difficult river of the world, the Padma River. Nobody has ever built any bridge under these circumstances. The double-decker bridge, 2-level bridge with the truss system is also a unique and rare design. Most of the bridges are single level, but this is the uniqueness of this design. The pile foundation, I spent a lot of time explaining the pile foundation and the challenges offered by that. This was never done in the history of engineering before Padma Bridge. The bridge has been designed for the most seismic condition, as I said. A bearing has the capacity to carry 5,000 tons, nobody ever thought of, heard of even. Scour was another major concern. None of the structure ever built in the entire world has to design for such a scour, like 62 meters. And of course, I explained the unique bank protection concept, the river turning concept, and the most expensive and most innovative design ever taken. Considering all this fact, I'm convinced that Padma Bridge can easily qualify as, next slide. This is my last slide. Padma Bridge is a modern engineering marvel. But again, we have to tell our story. We have to, nobody gives you a recognition unless you ask for it. So many of you probably will know that we are convening an international conference in Dhaka, Bangladesh, and the lead organizer is American Society of Civil Engineers. They'll be coming to Dhaka, Bangladesh. Their counterpart will be coming, and we'll be telling them about our great Padma Bridge, and we have to lobby actively to ASCE so that Padma Bridge is included in the list of modern civil engineering marvel for the 21st century. Thank you for your patience.
What a nice presentation. What a wonderful presentation. I wish we had many more marvels like that to talk about. Unfortunately, this is the only one that that we have in Bangladesh right now, and obviously the current government has a lot of credit to make it happen. Everybody knows the history that they are going through and they have gone through to achieve this distinction. Just one or two questions. We have time to go through a few questions. So
Sure.
The major questions are well, not so major, but lately we heard the news that a few accidents have been happening on the western end of the bridge near the toll plaza. So, any reason that's happening? Is it the driver's fault, or is there any difficulty with the bridge itself?
This is one area I really have to pass it because to me it looks like that the bridge design was in conformance with international standard from A to Z. So I cannot put blame to the design and construction of the bridge. Maybe our drivers, our people are trying to get used to this kind of structure configuration. It could be partly the fault of the drivers, but as far as the design of this bridge is concerned, it has followed all the international standard. It has followed what we follow in United States is called ASTO. They have followed the ASTO standard. They have followed the British standard. They have followed the European standard. If anything, this has been over-designed.
One other question is, the bridge has kind of a S shape, and also somebody pointed out that most of the very long bridges are a little bit elevated in the mid portion, and this one is flat. So would you please comment on those two?
Yeah, this is something, originally the idea was to build this Padma Bridge. As you know, that it has got 42 span. Original design was that only the middle 3 span will be raised. So the big ship can go pass through only those 3 spans. If that was implemented, then the middle portion of the bridge will be much higher than the other part. It will have a sloped up and down. But at one point or other, the decision was made, no, that is not good enough. We will make the bridge passable by the large ship in each and every span. So all 37 span inside the river has the same headroom, what I say, 60 feet from the highest water level to the bottom of the, that's why the bridge has one uniform slope, not raised up at the middle.
Oh, that's very smart. Then that means everything is high.
Everything is high. In any span, the ship and the barges can pass.
It can
It
pass.
is not and most of the bridges, they concentrate on the central part. But whoever took this decision, I praise him from my heart. He probably knowingly or unknowingly knew that the Braided River does not stay in one place.
Right.
So you have to have the provision for the entire width, and that's exactly what was done.
So this is definitely a significant milestone for Bangladesh. So how will it help industrialization and economy of Bangladesh? Any comments, please?
When the feasibility study was done by JICA, which is Japan International Cooperation Agency, they did the economic study and this and that, and they have concluded that this will benefit 29 districts of the southwest of Bangladesh. They were isolated. They are not connected to any major port like Chittagong or anything, or they are not connected to Dhaka. And that impeded the development of these 29 districts. Now, this bridge will open up that door. And according to the projection by JICA's report, that it will increase the GDP, gross domestic product, by 1.2%, which is tremendous.
Sure.
So they will have now access to Dhaka easily. They will have access to the major ports. Now there is a new port in Pier. They will have access to the Pier for transportation of goods for overseas, as well as there will be development of industries in these areas. Already Bangladesh has build a very large, the largest power plant in Pier, 1,300 megawatt. So those power can be utilized to industrialize this 29 district, and this bridge will be the link to carry their products all over the world.
So they're having a railway track on the lower level, and as far as I understand, train can go only one direction at a time. Is it possible that they could expand it to two-direction train in the future? And why was it done? Is it the expense or is it the engineering factors?
It's definitely the expense. When we talk about the expense of the bridge, we only talk about the bridge expense, and the bridge expense is roughly $3.6 billion. And that was totally funded by the government of Bangladesh.
Right.
Now, when we talk about the addition of the rail section, the cost of the rail portion of the bridge as well as the connecting railroad, because you just build the bridge, it is not connected to the internal rail system, it doesn't mean a thing.
Right.
The total cost of the connecting railroad plus the bridge portion is $4.8 billion.
Mm-hmm.
And that's being built as a BOT, build, own, and transfer. And China is building the rail portion, they will finance, and they will operate, and they will collect revenue for a certain year and then transfer to government of Bangladesh. So that way, the reason the cost was concerned, if you want to put two lines, the width of the bridge will become much bigger. And of course, the cost will be proportional to that. So it is a first concern is the cost, and the second concern was financing that also. So those two considerations made it this single track.
So recently there was an interview by our foreign minister, Dr. A.K. Momen, and he refuted that it's not China who built that bridge, and it's Bangladesh has built their own bridge. Any comment on that?
That's really laughable. Anyway, I know our foreign minister, Dr. Momen, very well. He's a good friend of mine, and I agree with him 100%. China was the contractor. China Major Bridge Construction Limited. They are the contractor. They were not involved in the design. They are not involved in solving the solutions. Right. When the problem came, they just said there's a problem. So and I have never heard in my life that a contractor claims, I am the builder of the, yes, you build it physically, but you are one component of the hundreds of people involved. And as far as I know, there are about 13 consultants involved in the design and solving this problem. So all those 13 can claim the same thing, that I built the bridge. So yes, we have to give them credit. They built this challenging bridge, but the credit goes to government of Bangladesh. The bridge was built by the government of Bangladesh with their own funding. China was the contractor. That's what you have to differentiate.
Now, I think we're coming to the end of the session, but I'm sure Bangladesh engineers have learned a lot on the construction side, because the gantry crane and all of those things had to come from China, hammers came from somewhere else, etc. Will Bangladesh down the road be able to manage everything on their own, including all the constructions? How long could that take?
I'm told that almost 2,000 Bangladeshi engineers got trained on this project, which is a tremendous thing. And of course, they will be able to utilize their experience and expertise for the future projects. That's the way we do. When I came to this country 50 years back, I had very little knowledge, but over the years, I gained the knowledge, expertise, experience, seeing how it is done. So this opportunity does not come to everybody's life.
Right.
And those engineers who have been involved in this project, they are lucky that they were given this opportunity to learn. And I'm confident they will be able to use their experience and expertise and build another Padma Bridge by themselves.
Right, right. And then one other thing is that only over a few days they raised so many crores of taka from toll, and some estimate mentions that it will take about 35 years from toll alone to get all the expenses back for the whole bridge. Now, is that an important factor? Should they be concerned about it, or I mean, why is that such a big factor?
I don't see why it should be a big factor. This bridge has a lifespan of, this was designed for 100 years. If you can recoup all your investment in 35 years, I think that's great.
That's great, yeah.
So a lot of the other structure, major structure, they try to recoup it faster. The fastest I heard is 15 years, 20 years, 30, 35 years is very common. If you can recoup your total cost in 1/3 of the time of the lifespan of this, so there is nothing to be concerned of. You should be happy and proud that we can recoup the money in 35 years.
Absolutely. Well, we are happy too. It's such a. I remember when I was in New York, the bridge on the Buriganga River opened, and there was a discussion that Japan built that bridge, so Bangladesh is just enjoying the fruit of it. And now we came a long way. Now Bangladesh has built their own bridge, so we couldn't be prouder. And a special thanks goes to the current Prime Minister, Sheikh Hasina. Without her initiatives, it would never have been possible. So we are really, really proud, and we are very thankful to the country, to the government, and the people of the country. They are tremendous, resilient people, tremendously resilient people. They are showing their ability, their courage, their capabilities, and the 2041 economic goal, it should be solidified in time. So we are very happy for that, and our special thanks to all the people who were involved in this big mega project in Bangladesh.
Ditto, agreed.
All right, so we'll try to have this in as many forums as we can. And with that, thank you, Sufian Bhai, for your kind presentation and expertise. We are very proud of you too.
Thank you, Anis.
Okay.
It's my pleasure.
Thank you. Bye now.
So you're stopping recording, right?
Yes.
Okay. Yeah, I got an invitation. You remember